Hi everyone, welcome to this multi-part series on sequence model for text data. Second video in this series. First one was the overview video. The link of that is given in the description below. In this particular one, I'll be talking about the insights of recurrent neural network, how they work, and what are the you know finer technical points on RNN. So the agenda is going to be first the understanding of the fundamental components of RNN, working of the RNN using some of the toy examples. I'll also talk about how the forward propagation and a backward propagation work. Most importantly, how the weights and biases are computed in RNN. There are different configurations of RNN that we will see what configuration is suitable for what purpose. A little bit of prior knowledge that you will find it handy to have is understanding of machine learning and especially the neural nets and a good knowledge about regression concepts, linear transformation. I'll be using Keras to illustrate the code examples, and we need to also get a fair understanding of embeddings and how text data is processed. So, what are the recurrent neural network? Essentially, a neural net to process sequential data using something called recurrence. We will see how this recurrence is achieved. In a typical neural net, we do not have a feature called recurrence. RNNs use the concept of recurrence essentially to summarize information across the sequences. So when you have sentences and then you process the sentences from left to right, then the model is able to persist the information. That means from left to right, it generates a memory vector. That is what the meaning of recurrence is. And that's what makes the RNN well suited for time series modeling or speech recognition and many of the sequential data processing. So one of the key distinct characteristics of RNN is the loop. So the way the training happens in RNN is a feedback loop. History of RNN, I mentioned to you in the overview section. It was introduced in 1980s, but it did not pick up momentum. It required some time because of the fact that RNN's sequential nature of RNN makes it slow. So, with the advent of GPUs and some changes to the model architecture, contributed to successful usage of RNN. Why it's called recurrent? The reason it's called recurrent is it is executing the same task over and over again. That means if given a sentence of 200 words, it's going to process the sentence from left to right, and exactly the same operation will be carried out for each of the word in the sentence. So the output of the RNN is not just the current input, but also the preceding values or preceding words. These two characteristics define the term called recurrent. Why do we need recurrence? Let's take an example here. One of the reasons is we need to build memory, or in other words, we need to build um, recurring context uh, for a given sequence. Let's take an example. I had washed my house. So when the model actually reads the token from left to right, it's going to generate the memory vector. But similar sentence, I had my washed a house washed. This is slightly different, but the meaning is also completely different from each other. And that is why the concept of recurrence is required. When you read the sentences from left to right and you aggregate at the end, that will give you a different memory vector compared to the memory vector that you get in this sentence. This is called gaining the deeper understanding or semantics of the text. Essentially, the deeper understanding is achieved through the memory vector that we compute uh, recursively. Let's do a little comparison with the standard neural net and recurrent neural net. In a typical standard neural net, we do not have something called memory. Given the input data, it is pretty much independent. It doesn't matter whether the samples are related to each other or they have a temporal dependencies or not. So in a typical neural net, you just provide the input data and connect it to the hidden layer, and there is no such concept of a memory for a given sequence. In contrast, in the RNN, you have a sequential nature of the data. So the data will flow from left to right, and each of the box that you see here in the green box would be processing the token or the word or whatever unit that you want to process using the RNN. So each of these boxes would be like a time step in the language of RNN. That differentiates the two. So why standard RNN, standard neural net cannot be used for sequential data? In a standard neural net, you are expecting to provide uh, the input data, which is fairly fixed, whereas in the case of sequence data, we do not have a fixed record size. And there is no such temporal information or a mechanism to process data in a temporal manner, and hence then also the lack of memory in case of standard neural net, and that's why we cannot use neural net for processing sequential data. How do we represent sequences in case of RNN? Sequences are non-independent, that means dependent. The input data is dependent in terms of time. So let's take an example here, and this green box is your RNN cell, and you provide the input here, and there is a corresponding output. Next time step, you will provide another input and another output, and so on and so forth. So let's take a sentence. Stars illuminated the night sky with their radiance. So you see there is a temporal association between the tokens or between the words. And the output here y1 would be illuminated. Similarly, output y2 would be D, and the output y3 would be night. So you see here there is a non-independent nature of data. That's how we present the data for RNN. Let's take a look at the structure and a typical structure and the flow of RNN. So you provide the input, and here is the RNN cell which processes the input and gives you the output. So that happens in a typical, standard neural net. You provide the input and it goes through the hidden layer. In contrast, it will be slightly different. The input will be time step, that means the word or a token. And the process is very much similar to standard neural net with a little bit of difference. And then there is a corresponding output. Now, the difference is here the input to RNN, or the process that will be carried out here in the hidden cell, would be for the input data as well as the previous data or previous time step. So both of these are taken into consideration. And since this is time step based, and hence there is a loop. So that means this means is going to be executed for as many tokens as you have in the given sentence. So there are a couple of flavors how you can design your RNN. One is a single layer. So let's say this is the input and this is RNN cell and output, and looping. So you can unfold into series of tokens here or time step. And let's say you have three tokens, so it will be three RNN cells here. And each of these cells will be carrying out almost similar activities like input and the processing. The processing here is dependent on the input plus the previous input or preceding input. Similarly, when it goes to the next time step, the current input and the output of the previous processing, and so on and so forth. So this is called single layer RNN. Let's take a look at what is the other one. So a typical RNN will have the input here, and like X denoted by xt. T means time period, and this is where the processing will happen. This processing is called hidden computation or hidden state. That essentially technically also means the memory of the network. As the process is being carried out, let's say at the time step 3, whatever you have computed will be called the memory of the network. And the output similarly can be obtained at each of the time step, or you can get one final input output at the very end. So that's your single layer unfolding. So you stack the bunch of sequences in terms of time step, and the memory vector will be initialized initially with a 0 value, and then it will be unrolled in terms of the number of tokens that you have in the sample, and that's denoted by here T. Okay. Now another flavor, multi-layer RNN, pretty much similar. You have the input and the hidden computation. You have one more hidden computation here. So that's one more, and then output. So this is called multi-layer. So you could stack as many hidden layer as you want. And pretty much the same, will happen in each of the layers. So given the input, a memory vector initialized, and likewise, you're going to compute the hidden state for each of the time step. And again, for this one, the output from this layer will go into the input plus the preceding input here, and these two will generate the output. Finally, the output can be obtained at the end. So this is called multi-layer RNN. Let's talk about how do we compute the activations in RNN. This is very key to understanding, typical sequential data processing. So a little bit complicated, and that also makes the RNN pretty heavy. Let's pay attention to how do we set up the input data to the RNN. The first step is to understand how do we represent the words. So the word, one of the method to represent word would be one hot encoding, which is let's say you have a given set of words in your text, 10,000 of them. So you can give a an index to each of the word. Let's say one, two, three, four, five, and up to 10,000, preferably in the sorted order. So that means the word can be represented with a vector with just one place. We'll be having a one. Let's say Harry. The word Harry will have one in this place, and similarly, the word Potter can have one in some other place. So this is called one hot encoding. So this is one of the methods that we use to numerically represent the text data or the words or token. As we will see, there are some limitations of this one hot encoding, namely the product of any two vectors, let's say, man and a woman or king, that will result in zero. And also the distance between any two vectors will be the same, which really not is something that we are looking at. So we need a better way to represent the input data. Uh, so that better method is called embedding. So that those are the two downsides of the one hot encoding method. The other method is to do integer encoding. That means you assign arbitrarily some number to these tokens. So this can give you a dense representation. But the method that we use typically in the sequence modeling is called word embedding. And again, embeddings are obtained using a different mechanism or a different trained neural net. Let's take an example. Let's say the word Obama. And by using a traditional method of vectorization, you could represent Obama having something like a sparse representation. For example, let's say you have 100,000 words. So this vector would be 100,000 element long, and it would have one in a particular place. In contrast to that, we would like a different mechanism here using a dense representation. We don't want to use 100,000 element vector representation, but rather a chosen number, and that number can be much, much, smaller than 100,000. So that's the, word embedding here. So the advantage of word embeddings are number one is the number of elements in the vector is way, way smaller, and still it gives you a very good performance. The other advantage is it gives you sparse to dense representation. So if you see here, this vector representation is very, very sparse. Compared to that, this is more like, continuous values, and this is a dense representation. So we use this kind of word embedding as input into our RNN. So what these embeddings actually look like? Embeddings are typically, floating numbers. Let's say, king, man, and a woman, and they are different in terms of the semantics and the meaning of king and man and a woman. And the representation for each of the token would be a series of numbers. These numbers are obtained through a pre-trained model. And for example, Glove or FastX or Elmo or Transformers or BERT. But in all cases, the embeddings are nothing but series of numbers, floating numbers. So just to illustrate the idea of embedding, so let's see, we have these words. And if you notice, all of these words are different, but there could be some dimension where the values may be similar for each of these words. and that is shown by using this particular box here. But if you look at a woman and a girl, you'll see the vectors are pretty much similar to each other. And likewise, if you look at a boy and a man, these two vectors also look similar to each other. The exception would be water, so that looks very different compared to the other vectors here. So why do we need word embedding in the RNN? As RNN, the purpose of RNN is to generate semantically similar vectors or meaning. So our embeddings provide you exactly that. And embeddings also help you generate the contextual sense from the input data. At the same time, there is a huge benefit because of the dimensionality reduction by using word embedding. Overall, it provides a good generalization. Let's see now that we have understood the embeddings, and let's take a look at how RNN cells are unfolded given an input sequence. Let's say this is your RNN cell, and these cells as you notice, there are hidden neurons here, and that will define the memory of the network. Here is the input being given and corresponding output generated from the hidden RNN cell, and we initialize the memory here, which is called activation with zeros, and the output from this cell would be A1 in the time step 1, and we have the next input and the output here, and correspondingly uh, or rather similarly, you'll have the computations for the other time steps. So this is very typical of RNN unfolding. And notice at each of the time step, we will be feeding the embeddings here. Let's now take a look at how the forward propagation actually happens in the RNN. At the time step 0, we will provide the first token to the RNN cell. And I'll be describing all these weights matrices and the bias matrices. As you notice, we're also going to initialize the memory vector and the output. Okay, so now the new pieces are your weights matrix here and the weights matrix here. There is one more weights matrix which will show up here now. So there are three weights matrix that is used. Now what they do is when you provide the input here, let's say x1, that x1 will be multiplied, which is basically x1 is nothing but your embeddings, uh, let's say 50 dimension embedding, that will be multiplied with the weights matrix. So the weight matrix also needs to have 50 dimensions. So when you initialize the weights matrix here, that would be at one end, it will be connected to the input 50 dimension. At the other end, it will be connected to the size of the memory. Let's say the size of memory is 64. So this WAX will be set up as 64 times 50 as the weights matrix. Likewise, the WAA, which is the activation matrix from one time step to another time step, and let's say we are talking about 64 neurons here. So this would be 64 times 64 dimension. And likewise, you have weight matrix, which connects your activation to the output. Let's say you want to have the output in 10 dimension. So this would be connected to the activation, which is 64 dimension anyway. So this would be 64 times 10. So let's look at the computation at the input level. What happens is you are providing the you are providing the input, and this is going to be multiplied with the weights matrix. As I mentioned earlier, there would be a previous or preceding input as well, which is going to be your initialized zero vector, and this is multiplied with the weights matrix WAA. and that gives you the activation A1 in the time step 1. So let's take a look at what happens in the output. So the output is pretty much the same here. You have the activation. So this activation goes to uh, this layer, and then you multiply with the weights plus the bias, and then you apply some activation like sigmoid and softmax. Why sigmoid and softmax? Because this is the output. And here typically we use tanh and ReLU. This pretty much summarizes what really happens in the RNN cell, and exactly the same thing will happen in the other time step as well. So I just copied it here, and for the other time step is exactly the same thing that happens. So let's talk about the weights and biases now, how they are getting computed or adjusted, or how they take part in the computation. So let's say, this is where the computation will happen for a given time step or given token in the input pattern here. So let's say x1 at time step 0, and let's say the x1 is defined with a dimension of 3, for example. So this value or the word will be 1 time 3 vector, and this needs to be multiplied with the weights matrix, and this weights matrix is connecting the layer with the input. So this will be, let's say the number of neurons is 7. So this would be 7 times 3. So this vector size would be 7 times 3. And the memory size, let's say we initialize with 7 here. So that's the memory of the network. And the weights activation, for activation, this would be 7 by 7, because the next time step also will have this 7 neurons. So this will be 7 times 7. And the bias is there's a bias to the those 7 neurons. So this is also going to be in the same specification 1 by 7. So the final activation, or the activation that you get out of the hidden cell, would be the same formula that we just saw in the previous one. Given input with the weights and the activation from the previous cell and the weights here, and there is a tanh and ReLU. This pretty much happens exactly the same way in all of these cells. So in the previous step, we saw how the input is converted into a memory vector on the context. Now the output has to be computed with the help of a memory vector. So this part we have seen in the previous slide here. Now the output, which is basically this activation here, that will go into the computation of the output. So that's the memory vector, is essentially a vector or representation in terms of the number of cells that you have in for a particular time step. And this input will be multiplied here with the weights YA, which is the output is Y, and the A is the activation. And again, the dimension is dependent on the dimension of the activation layer and also the dimension of the output that you want. Let's say the output dimension is 3, so this would be 3, and 7 is anyway the dimension of the activation layer here. So 3 cross 7 would be the dimensionality of the weights matrix. And again, the bias is for the output. So let's say the output dimension is 3, so this is also going to be in the 3 cross 1 shape. And this will take part in this linear transformation called, the weights times the activation plus the bias, and then we apply some activation, a suitable activation, let's say sigmoid or softmax. So this defines these two steps are the main computation that happen within the RNN cell. The first one is the computing the activation itself, and then those activations are used to predict the output. So essentially, this is what is your computations in terms of the matrix here. So let's talk about the backpropagation. Pretty much similar concept in terms of theory is very much similar as we have seen in the standard neural net. Just the formulations are going to be different here. The backprop is again based on the loss between the actual output and the predicted output. So how the loss computations happen is for each of the time step, you're going to predict the output, and then with the predictions, you're going to compare the predictions with the actual, and that will give you the loss here for each of the time step. And then you're going to aggregate all of these losses into a combined loss. Now, this is where the trick is used. So we're going to use this loss function essentially to do a gradient calculation and the adjustment required in the weights matrix. So that's going to be done at the last time step. And once you have computed the weights and biases, those are simply going to be copied to the other time step here. So this makes it pretty fast, in terms of or rather, it makes it efficient, in terms of how you can use the same matrices across the time step. So to illustrate the loss function, let's say these are the words and these are your embeddings. So with the given input, let's say these words, and we will push these words into the RNN network, and we will carry out the forward propagation. So that means, let's say the word is D, and we would like the prediction to be zero point 0.1 and zero point 0.2, and likewise the output is the current input, and we want the prediction or the actual output to be this embedding, and so on and so forth. And what we do in terms of the loss function is to compute the differences between the predicted value and the actual value, and then you square them just to illustrate the basic idea. And then you sum them up in terms of cumulative loss function here. And then we use this value to compute the gradient, and we're going to update the weights. So that's pretty much happens in the RNN cell using the forward propagation and a backward propagation with a little bit difference compared to the traditional neural net. So to summarize the key points about the RNN here, at each of the time step, we're going to have the weights. Now those weights are same across the time steps. Essentially, RNN will perform the same task over and over again with different inputs, same type of task. And this reduces also the number of parameters that we need to learn from the data because you're going to copy the weights matrix for each of the time step. You need to compute the gradient and adjust the weights only once, and then we copy that to each of the time step. So these are the key points in terms of RNN models. Let's recall some of the salient points in terms of application usage. Let's have a deeper understanding on those that will help us build NLP applications. So this was our RNN cell here, and then we generated the activations at this point. We also generated the activation at this point. So this is called activation at the hidden layer, this particular one A3 time step 3. So this is called activation at the hidden layer. And essentially this activation follows the computation that we saw earlier. Just one second, let's go back. Yeah, so now we're going to compute the activation A3, which is going to be the current input, which is whatever x2 or x3 multiplied by the weights, and then the activation from the before step multiplied with the weights matrix. Bias term is added, and then apply tanh or ReLU for nonlinearity. So this is giving us the activation at the hidden layer. And we use this in some applications, which we're going to talk about subsequently. Now, the activations at the output layer, this is also one of the feature of RNN, and our output activations that we get follow the calculations. Let me go back one step here. Yeah, so this is again the activation from the current layer and then multiply by the weights and the biases. So this is going to give you the activations at the output layer. So both are important features of the way the RNNs actually work, and we will make use of those in our subsequent demos or use cases like text classification or sequence generation. So how we handle those activations in Keras is a parameter called return sequences. So when you mention return sequences equals to true, and that's going to return the sequences or the activation or hidden state at each of the time step. And you're going to get back those here by setting the return sequences to true. By default, it is set to false. Now, one more parameter that helps us with getting the final hidden state is called return state. By default, it is set to false, but you can set it to true if you want only the final hidden state at the end of the time step. This is useful for applications like text classification or sentiment analysis. Some of the popular configurations of RNN. So there are different ways you can set up the RNN. One is many to many. That means many inputs and many output. That means, let's say the video classification, you have frames, and for each of the frame, you want to generate corresponding output. So that would be an example of many to many. So in this many to many, the number of inputs or number of outputs are same. You could also generate many to one, for example, the input data, and that is consisting of many tokens, and you can generate one final output. This is what we will start with in our use case with the sentiment analysis application. There are other many to many configurations as well. For example, number of inputs and the number of outputs are not same, and that is useful in machine translation or a language translation. This we will discuss in detail in a separate playlist. So next I'm going to be demonstrating Python code to illustrate how the memory vectors are computed and what is return sequences, return states, and simple classification example using RNN. Thank you.